Welcome to a video by Exact Education. The purpose of this video is to explain the operation of a step-down transformer. The primary, the input coil, has got 625 turns. The output coil, secondary, is 120 turns. That gives a turn ratio of 0.192. So we can see the waveforms on the oscilloscope. We've got the voltage going in, the large amplitude, the voltage coming out, the small amplitude, and the amplitude coming out is significantly smaller, and we can measure it on the oscilloscope, digital oscilloscope. It will give RMS readings out. We're also getting RMS readings on the meters on voltage going in. We'll call it 13 volts RMS. Voltage coming out, 2.46 volts. We can measure the current going in on the primary side, 226 milliamps. Current coming out on the secondary side, say 86 milliamps. We have two 12 ohm resistors in series making a load of 24 ohms. We've got a low voltage power supply here that's stepped it down. The maximum we can get out is about 13 volts RMS so that it's safe to wire. Extra low voltage below 50 volts. Transformer here, 625 on the primary, 120 on the output. So the question would be, is we have a turns ratio of 0.192. So do the meters match up? We've got 13 volts RMS, 2.47 coming out. So that gives us, if we divide those voltages, 0.19, that does validate the turns ratio as stamped on the coils. What does the oscilloscope say? Oscilloscope says 13 volts RMS on the oscilloscope, 2.5 volts RMS coming out. Divide those two numbers, 2.5 divided by 13, give us 0.192. So we're just validating again that the voltages we're getting out do match with the turns ratio. What I'll do now is I'll break the output circuit so that there's zero current flowing in the secondary. We can see that on this meter, and we're now got a different current in the input. It has gone down. The primary voltage not changed, secondary voltage not changed. So let's analyze these currents and come to some conclusions. So when we have the transformer on no load, which is this arrangement here, there is zero current flowing in the secondary. There is no electrical circuit between input and output. It's linked magnetically by magnetic induction as per Faraday's law, minus N times the rate of change of flux. What we can see here is we have 17.7 milliamps flowing in the primary. This current is the magnetizing current of the transformer. It's the no load primary current, which is the magnetizing current, which is simply there to provide a magnetic field on the primary that links into the secondary so that we get transformer action. This current does not do work. This current is also 90 degrees out of phase with this voltage. These are meters, so they only measure size. When we're in AC circuits, we have to analyze circuits in two dimensions: size and phase shift, size and angle. Meters only measure size, the amplitude of the current. So we're on a no load situation. When we're on no load is used for testing core losses. What do we mean by core losses? Core losses in a transformer are the hysteresis loss, the eddy current loss. Hysteresis and eddy currents result in heat loss and can be given by an equivalent circuit resistance. And this magnetizing current of 17.7 milliamps is out of phase with the voltage. So the out of phase is important because, as we said before, when we're working out currents, we need to do a phasor addition, size and angle. Complex numbers, two-dimensional addition. If I now then go back and complete the circuit, put the circuit connection back in, we can see that we have approximately 89 milliamps load current now on the secondary side, and we now don't have 17.7 anymore, we now have 26.8 milliamps on the primary side. So why would the primary current increase? So the primary current increases because there has to be a rebalancing effect when we add a load. When we've got a load on the secondary, we now have a secondary current. When we have current flowing, we must have an associated magnetic field. So we now have two magnetic fields. We still have the primary circuit magnetic field that's driven from the power supply, and we now have a second magnetic field which has been induced from the primary. That secondary magnetic field that's been induced by Lenz's law has to oppose the change that caused it. So what now happens is there's a rebalancing effect whereby the load current on the secondary has to be reflected onto the primary, and the primary current has to then increase. The primary current, which is there, now has two components, not just the magnetizing current, but it also has the reflected load current. That reflected load current is in phase with the voltage that's induced on the secondary because it's a resistive load, but it's out of phase with the magnetizing current. So we now have a phasor addition of currents. They're not, the primary current is not physically separate, but it now has two elements, two components. It has a magnetizing current, and it also has a reflected load current. So in order to work out from theory what the primary current should now be on load, we now have to do a phasor addition of the magnetizing current and the reflected load current. The load current is 89 milliamps. You can see that on the meter. Using the turns ratio of 0.192, the reflected primary current for the load will now be 17.1 milliamps. That 17.1 milliamps is 90 degrees out of phase with the magnetizing current. So in order to work out the new primary current, we have to do right angle triangle Pythagoras. In order to work that out, we have a phasor diagram. We have 17.7 in phase for the magnetizing current. We have a 90 degrees out of phase reflected load current to the primary of 17.1. Square those two numbers, sum them, take the square root. The prediction from circuit theory is the primary current should now be 25 milliamps. What we get out is, what we can see is we have 26.8. So it's not exact, but it is within reasonable of close to the predicted value of 25 milliamps. So why would it not be exact? It may not be exact because the assumption is that the magnetizing current is 90 degrees out of phase. The reality is, because of the core losses, it won't be 90 degrees. It will be somewhere between 80 and 90 degrees. And that needs to be taken into account in terms of the calculations. So to summarize, what we've demonstrated is we've demonstrated transformer action on no load. You've got a magnetizing current that's simply there to provide a magnetic field. It does not do work in itself. If we connect loads into there, the primary current increases, and it increases because it has to supply the resistive load current in this circuit. So the load current then gets reflected back onto the primary, and the reflected ratio is the turns ratio but when you're calculating the current, it has to be a phasor addition. The meters don't show the phase, they simply show the amplitude. Thank you for watching. Please subscribe, please comment.